All right, welcome everyone. Thank you for attending this session. Last day of KubeCon in the afternoon. I'm glad you all could make it. So today we wanted to discuss how you can optimize scheduling for large-scale, big data distributed jobs. And yeah, I've got a partner in crime. We'll go through introductions as well in a bit. But before we do that, I just want to do a quick show of hands here. Who here has ever stared at a pending status for a job that you know is urgent? Okay, keep those hands raised if that job was a Spark job or a machine learning, AI, array job. Okay, great. Okay, great to see there are some people familiar with that situation. We've all been there. We're running the most advanced high-performance workloads on a scheduler, if you were using the default scheduler, that was primarily designed for web applications. So today we're going to discuss why that's a problem and what the community is doing and what we are doing at Cloudera with our Unicorn scheduler to fix some of those gaps in optimizing the scheduling issues for big data workloads. So just quick introductions. My name is Rahul Sharma, and I'm the Director of Product Management at Cloudera. I lead our core platforms that run on Kubernetes, both in private and public cloud. We have a bunch of data analytics products and applications, from data warehousing, data engineering, to machine learning, AI, and even streaming data. And I'm joined by Wilfred.
Yeah. Wilfred Spiegelenburg. I'm principal engineer. I do the development of Apache Unicorn and the quota management side of that. I'm part of the ASF, the Apache Software Foundation, as a member, committer in Hadoop. I've been around in all these yarn and scheduling things for years and years. So.
All right, thank you, Wilfred. So we'll be covering this presentation in 3 parts. The first part will be focused on just an introduction to how the default scheduler works. The second part will be focused on defining some key terms about how the term gang scheduling is getting redefined a little bit in the community as well. We'll paint the landscape of the available schedulers available in the Kubernetes community today. And in the third part, we'll talk about the key gaps that we see in the default scheduler and how we can fix those with some of the schedulers that are available out there, including Unicorn. And then we'll close it out with a demo by Wilfred about Unicorn's key features. So let's dive in. So what does the Kubernetes scheduler even do? So Kubernetes scheduler is basically a key component of the Kubernetes control plane. And as in when you submit a pod or a job, it basically looks for those submitted pods, and then it schedules the pods, it schedules those newly created pods to available worker nodes in your cluster. How does it do that? It basically watches for the pods that are submitted, which are initially in a pending state. It then goes through a 3-phase process, which is the first phase is filtering. It filters the incoming pods, looks at the various filtering criteria, such as the resources that are set in terms of CPU and memory. It looks at if there are any hard constraints that are set in terms of node selectors, tolerations, taints. And then based on that, it goes into the next phase, which is scoring. Then it assigns a scores to the pod. It looks at the main goal of the scoring stage is to most optimally utilize the resources available on all the worker nodes. And then based on that, it assigns a score to that pod. Once that score is assigned, it then binds the pod, where it sends a signal to the API server. The API server then basically does like a commit action on that score, updates the pod config, and the kubelet then actually schedules the pod. So we do see that there are certain limitations of the Kubernetes scheduler, especially as it relates to running large-scale distributed data applications and large-scale data workloads. Starting with limits and quotas set for resources. So we do see that the key quotas that are set are not natively part of the scheduler. These are add-ons that you can add to the scheduler. The enforcement of these quotas is also not done at the time of runtime. It's done at the time of creation of those resources. And then these quotas and other limits can only be applied at the namespace level, not at a group of pod level or not at an application or workload level. And that leads me to some of the limitations that exist with actually scheduling the pods, where all of the incoming pods are treated as one large queue. There is no concept of an application of a group of pods being scheduled together, which means that there are also not as many options available to change the default scheduling behavior. So how does that work? You submit a request to run a bunch of pods or a job. They come in a single queue. They are filtered, scored, and then bound to one of the worker nodes. And then the pods can be preempted based on the criteria that was set within the YAML. So those are the sort of the generic limitations of a default scheduler. Now I want to talk about some of the challenges that we see with running large-scale data applications with Spark, Ray, or any kind of AI and machine learning training jobs as well. So one thing we see pretty often is resource contention head-of-line issues, pretty common. With Spark jobs, there are many executors that are involved in often completing a job. Each of the executor runs as a pod, which requires significant resources simultaneously, and the scheduler inherently is not aware of the resource requirements of the entire job. It only accepts a single pod individually, so it doesn't look at the resource requirements of an entire job. So that's a key gap that we see. There's also challenges relating to poor data locality and shuffle overhead. So Spark really thrives when data is processed where it resides. The default scheduler doesn't natively consider data placement when assigning the executor pods. And then if the pod that is being scheduled on a worker node is far away from the data, from where the data resides, that can result in suboptimal resource utilization. The job wait times can be much longer, and that causes a major problem for data engineering teams. We also see issues with inefficient gang scheduling for stages. So Spark often runs in various stages. At each stage, there are a bunch of executors that need to run. And if there are only a subset of executors that are scheduled and the others are not, again, that results in suboptimal resource utilization and extended job runtimes, which is, again, suboptimal. We also see issues with inefficient GPU and accelerator sharing. In the default Kubernetes scheduler, a GPU is treated as an atomic unit, meaning that you cannot share one GPU with multiple pods. You have to assign a whole GPU to a pod. You cannot share multiple fractions of a GPU with multiple pods. So that is a key limitation that we see as well. Also, topology-aware scheduling. That is another key challenge that we see, where especially as it relates to NUMA, non-unified memory access, in terms of scheduling pods that require GPU resources, if the pod that is scheduled to access a GPU is not in close proximity to the CPU as well, and the PCIe bus connection is not a high bandwidth connection, that will also result in suboptimal performance. So that is another key limitation that we see with the default scheduler as it relates to AI and machine learning jobs. So while there are these limitations and challenges, there are opportunities to improve upon these challenges. And how you do that is thanks to the extensibility of Kubernetes. You can design your own APIs, you can write your own scheduler, and you can plug that scheduler in, which can work either with the default scheduler or it can totally replace the scheduler. So what are those opportunities? One of those opportunities is writing workload-specific scheduling logic. So for example, for Spark, we would like to see that it is aware of the job phases, it is aware of the data locality, it is also aware of the fact that there needs to be gang scheduling. All of the executors need to be scheduled simultaneously, and if any of those are not, then that would result in suboptimal performance. For machine learning or AI workloads, it means understanding the GPU sharing models, multi-tenancy requirements, and specific needs of distributed training workflows, like distributed training frameworks like TensorFlow and PyTorch. Another key opportunity that we see is advanced policies with true gang scheduling, which ensures that all the parts of the distributed job start together and not broken out, so that the job is executed in the most resource efficient way possible. And it also takes into account quota management, preemption, fair sharing policies as well. And then lastly is the ability to integrate into external systems. So these external systems could be storage systems for better data locality hints, integrating with cluster autoscalers in a more intelligent manner, and provisioning resources in a more optimal way. So with that, let me hand it over to Wilfred to cover some of the key scheduling terminology and cover the scheduling landscape as well.
Thank you, Rahul. That's gonna, okay, let's hope that it stays. Thank you. So first part of the scheduling terminology, let's go and have a look at the gang scheduling that was already mentioned here before. Because gang scheduling is a loaded term. What is gang scheduling? Different people understand different things about gang scheduling. For instance, the way that you define gangs. How many gangs do you allow within an application? What's the failure policy? If one pod fails, does the whole gang fail? What happens? How do you do all those kinds of things? Sizing. Do you define a particular size beforehand? Does it have to use all those pods, or is it dynamic? Can you have less or more, or can you just see the gang as a starting size and then grow above that, things like that. So with all these kinds of differences in there, different people or different groups implement different strategies, implement different things within the scheduling setups. We'll see that a little bit later. Then the other thing, because we're talking a lot about Spark, and that's a lot of the big data workloads that are being run are Spark. In the community, or the different communities, we've got different operators to help run those Spark jobs for us, because Spark itself has only limited knowledge of Kubernetes in the background. It's not fully integrated with it, so operators are written around it to help you run your Spark workloads nicely on Kubernetes. Currently, there's really three around. That's the Apache Spark operator, which is reasonably new, only been around for about a year or so. Then the Kubeflow Spark operator, which is the original Google Spark operator, which was handed over to the Kubeflow team about a year and a half ago. So that's the second one. And then the third one is the Stackable operator. That's another open source operator from a group in Europe. And they have written a whole Hadoop-based ecosystem with all kinds of operators and all kinds of things. So that's the three that are around. Which one do you choose? It's not that easy. One is written in Go, that's the Kubeflow one. One is written in Java, that's the Apache one. The third one is written in Rust. So if you want to do anything and you want to make any changes, depending on what language you write in and what language you're familiar with, you can choose one. Then the license. The Kubeflow and the Spark operator from Apache are Apache licensed. Free and open, you can do whatever you want. The Stackable one is an open source license, more of a business license that you have to contribute back the info, the changes that you make. So you have to publish them. You can't keep them for yourself. So again, depending on what you do, you might want to use a Spark operator. You might not want to use a Spark operator. There's been a good talk from Damon a couple of hours ago where he explained what they did and how they did it at Airbnb, going into a lot of detail around all of this. Okay, so with that in mind, we've talked about the gang scheduling, we've talked about the Spark operators, but now let's look at the scheduling landscape that is around. We've got a number of schedulers around, and of course we start with the default scheduler as it is there within Kubernetes. So the default scheduler is set up to schedule a pod, get it running, and that's it. It looks at a pod, one pod at a time, one queue, It's got DRA support for handling a couple of nice other things. Preemption is priority-based, no opt-outs, limited, focused on services, mainly. Then we've got queue, a controller on top of the default scheduler. It doesn't schedule the pods itself. It just handles queuing of a group of pods or multiple groups of pods outside of the scheduler, and based on quotas in the queues that you set up, it releases that set of pods to be scheduled by the default scheduler and get it running like that. It can do something similar to Gang. It's not really Gang. They officially say they don't support Gang. Preemption is also slightly different. It preempts based on the group of pods. Yes, it uses priorities, but it also looks at the quotas and things like that you set up in the queues. The queues, all of themselves, are hierarchical, and they've got quotas set up. So different to what the default scheduler does. Then there's another two schedulers around that are used by a lot of people. Start off with Volcano, probably the oldest one. Came out of the Cube batch setup. That's where the code originally started years ago. They've got a hierarchical queue set up with quotas, with different ways of doing things. They fully support gang scheduling. They've got all kinds of nice ways of sorting pods with priority, fair scheduling, doing all that kind of stuff, so that's more advanced. It completely replaces the default scheduler from the recent releases. Priority-based preemption, again, based on quotas that are there in the queue, but only priority is taken into account, nothing else. And then the last scheduler that we'll look at beside Apache Unicorn, which we'll look at later, is NVIDIA's Kai, which used to be the Run AI scheduler. They've now pulled it back into NVIDIA completely, which is also a full replacement of the default scheduler. It does hierarchical queues, although in one place it says it can only do 2 levels in the hierarchy, and in other places it says you've got multiple, so there's a bit of a discrepancy there. Not sure, I haven't tried multiple levels, I know that 2 work. They've got a number of different quotas around. Terminology is slightly different than all the other schedulers and queuing systems use. And they're focused on GPU sharing and GPU-based workloads that are running. So one of the things that was mentioned by Rahul before is you hand out a full GPU. In Kai, what you can do is you can say, give it 0.1 of a GPU, and then it gets run on the GPU. And you can do that for a number of applications without needing to hardware split the GPU. Problem with that is that if one job crashes, it takes down all the other jobs on the GPU also. So there's no separation within the hardware. So that's a slightly problematic point. Similar to what Volcano does, Kai uses the CRDs to do the gang scheduling for it. It creates a pod controller and a pod group and does gang scheduling based on all of that. One thing that it does do, and that goes back to that gang scheduling definition in the beginning, it allows you to have a flexible gang. So you say minimum of 3 pods, a maximum of 10 pods, and then based on the amount of quota that is available and the load in your cluster, the set will increase from 3 till 10 and will get preempted based on that, what's running. That's a nice feature. Don't know how that affects the full runtime of the whole application, but it does work. Now, if we then go and with all this in mind, we've got the default scheduler, Volcano, Kai, Q, and Unicorn. What are the gaps? So the gang scheduling side of things. Default scheduler, no gang, nothing like that there. But they're working on changing that. The first thing that they added on top of that was the leader work set. Fixed gang, one leader with a number of workers beside it, and that runs as a set. And that's how they currently do their gang scheduling. They've got 2 caps open at the moment. One is for full gang support in Kubernetes. It only just started about 2 months ago, so there's not a lot of detail yet there. The first question that they were struggling with was that whole point about what is the gang? How do we define the gang? Where do we put all this information? So, opportunistic batching is something similar like that, taking a little step back. Next gap that we see is the queuing. All the schedulers have got the quotas. Kubernetes enforces quotas beforehand, so you don't really have queuing. Queue does that by pulling the pods outside of the scheduler, holding them, and only really creating the pods when quota is available. Namespace quotas are still around, so you still have got a little bit of a problem. How do they interact? What happens when queue releases things and the quota is not around? So also slightly problematic. Because of that, they've just raised 2 new caps again to fix those problems. Again, not a lot of detail yet because they're only, again, a couple of months old only, so it's a changing landscape at this point in time. The third cap that we see is preemption and multi-tenancy. So when you look at multi-tenancy, you've got multiple groups running your workloads in the cluster. When you look at the normal preemption side of things in most of the schedulers, or now all of the schedulers that have just been mentioned, is they look at priority, they look at the queue, and that's it. So if you have not split your tenants over multiple queues, then one tenant preempts another. There's no shielding, nothing out there. Priority is the only thing, and you don't know what happens after that. Even with the leader work set, all these new things that are adding on top of each other, there is no protection of a leader. So if you kill the leader, the workers fall over. That could be costly. So that's not really something that you want. It's all based on priority. So yeah, they say, oh, then you need to give the leader better priority, blah, blah, blah. So it comes back to a management task that you need to do. So fixing the gaps, and what did we do from the Unicorn side to work on all these things? Now, Apache Unicorn has been around for 5.5 years now, almost 6. We started off coming out of the Apache Yarn kind of setup with multiple queue hierarchies, multiple tenants, preemption based on a queue, shielding, all these kinds of stuff. So what we looked at was getting the functionality that we had in Yarn and put that into a scheduler for Kubernetes. I've done talks on this before, probably about 2 or 3 years ago. We went into a lot of detail on the designs and all that kind of stuff. So if you want to look at all of that, please go and have a look. To quickly go over this, what we do is we do workload queuing. So we implement quotas within the scheduler. So no namespace quotas that we use. We let you create the pods and we keep the pods pending up until there's quota around. We implement gang scheduling. We do all 4 different types that were mentioned in the beginning. So full failure, all the things, we've got them all implemented. And we are application aware. So that's something that came up, and the working on a workload concept in the Kubernetes scheduling to release pods at the same point in time that will support the gang scheduling, and it also helps on the preemption side of things. So we've got full hierarchy for queues, multiple levels, quotas on different levels, grouping of quotas, moving up through the hierarchy. So if we look at the setup that we've got here, then on the root queue, we've got a quota that's the whole cluster that gets dynamically calculated based on the nodes that are registered. I have my usage, that is the pods that are running in the leaves on the end, and when I calculate all that information and I push all that information up, then I see the usage going for the sales, for instance, is the sum of what runs in the batch and in the production below that. And then if I go one level further up, I get another level. The org is the combination of sales and marketing. So, and it goes all the way up to the root. And at every single level, if you set a quota, that gets enforced. We do quotas for not only the queues, but even for specific users running within the queues. We then also looked at preemption and then said, okay, in the same hierarchical structure, we do preemption, and we look at how that works. To allow us to do multi-tenancy, we can say, okay, the group of sales, we fence that off from the rest of the system. We don't want people in sales doing something for the marketing, and we can do that at different levels and making sure that we don't allow the marketing team to preempt workloads that are running for sales. So if you go the step forward. So if I've got a workload running within the production with a high load priority, then I can preempt out of the queue that sits besides it. So the production can get from the batch. The next step would be looking at, okay, I've got a high priority workload coming into the batch on the marketing, but because that is fenced, it's not allowed to preempt anybody else. So we shield queues from each other, make sure that they can't affect each other. And then if we've got a high priority workload sitting outside of the fence on the top in the system, that is allowed to pick off any other thing, because, hey, my system stuff needs to run. That might be a daemon set or something else that runs in that queue, and it has to run, so it can pick off any bit that's needed. Okay. So let's see if we can get that in a little demo also. I've set up a little script from there you go. So I've set up the same queue structure in Unicorn. It's just a simple YAML file. Defines everything from the fencing to the quotas. Pretty simple hierarchy in all-in-one file. And if we look at a workload that runs really simple, I think we use a sleep job or a pause job in this case, and we've got different jobs and different things that get submitted. Now, the first thing that I'm going to do is I'm going to create some jobs in the system queue, and I've got a And I've got my queue system all running up here. And now I need to. Yep. That's my system stuff that runs. It's all going to be fine. That's all done. And then the next step is I'm going to submit some jobs in the batch queue that will get started. And we'll see the same kind of information, and we count towards the max, we count towards the pen. So we've got a pending job sitting here in the cluster because we've got a maximum quota set. So 2 running pods, 1 is pending, waiting for resource to become available. We submit in the other queue, we'll see the same thing happening in that queue. And because of time, we'll go through, and now we're going to submit a job in one of the other queues that is going to preempt. And I hope that I'm on time, that I can still show that it's still waiting. It's not preempted yet. Where's the preemption go? Yep, there we are. So after about 30 seconds, something that's configurable, we kill some of the workload that was over the guaranteed quota, and then we start up, and that automatically starts the pods in the queue that are below its guaranteed. And I think so that was a really quick demo from what happens. All these slides and everything is available. Then as a summary for what we've done and what we've looked at, batch workloads, we've got a high churn. That's something also that's completely different than what we do for anything else on Kubernetes. High churn of pods, gang scheduling and quota management, things that we really want, with multiple tenants, multiple groups that are running workloads on the system. But we still need long-running workloads also, which might need gang scheduling. For instance, with the AI serving the inference and all that kind of stuff, you might want to run that in gang setups. LLM services, gang-related setups we want to do. We have done that. It was a big question. Currently, we're looking at making the configuration much easier. All the other schedules have gone through CRDs, and which means you sometimes have got 10, 20, or 30 different CRDs that you need to maintain. From our side of it, we've always said, let's keep it simple, 1 YAML file, configuration map, and annotations on the pods, and no CRDs that you need to maintain or anything else. And the last thing was the complex interactions. Yeah. So with all these things in mind, we're trying to extend what we do within Unicorn. We try to pull in whatever gets generated from the community for leader work sets or whatever, and build on that, making it as easy as possible to use, giving you queues in hierarchies with multiple levels of quotas and things like that. We're out of time. Don't think if you've got questions, please come to us. We'll answer. We'll be around for a bit. Thank you.